So we've been looking at solutions. Now we can start to calculate different types of concentrations, sorry, squeaky chair, in our different solutions. But there's a special class. We've mostly been looking at solid and our aqueous phase solutions. We take some solid powder and we mix it in and we make a solution, how we can calculate those concentrations. But this is not the only type of concentrations solutions we can have. Another special class that has some unique properties are solutions that contain both a gas and a liquid, where we've got gas particles dissolved into the solution. And this happens pretty frequently because as you would think about it, how would fish be able to pull oxygen out with their gills to be able to breathe? How else would you get carbon dioxide or fizzy bubbles into your soda pop beverages? And so there's got to be some way we can figure out how concentrated are those gas particles inside our solution. That's kind of our next piece here is our Henry's law. But if we think about our kind of solutions that contain these types of setups, what would your solute be? Well, it's usually the thing we have less of in solution. The solute would be your gas particles. Your solvent would then be your liquid. Most oftentimes it would be water or some other solution in that nature. Typically it's water that we're trying to dissolve that gas into. Now let's think about this. Water is polar, right? We got kind of a polar distribution on our bent arrangement of water. Oftentimes our gases, if we think of O2 or H2, N2, our methane gas, all of these gases are nonpolar and they're really little, which means the only attractive force that they would exhibit, our only intermolecular force, is our London dispersion forces. As a result, this is why when we kind of crack the seal on our soda pop, a lot of the gas particles escape because they're non-polar. The water's polar, they don't particularly mix well. And so in order to get the gases to stick, there's kind of two options. The first option to get kind of increase your solubility is actually to cool down the gas particles. Oh, I think you're saying, wait, no. If I want to dissolve more sugar into my coffee or tea, I heat it up. And that's true for solid solubility, but for gases, it's actually an indirect relationship. It's inverse. As temperature increases, your gas particles move faster. And as they move faster, the ability of water to kind of get its attraction going or get that London dispersion force decreases. And so as your particles move faster, more of your gas escapes. You've had this happen to you if you've ever left your soda pop in a hot car and you come back and it's flat, right? All your gas particles get excited and they escape out of the surface of your solution. The other way we can kind of effectively change the solubility of our gas liquid solution is via pressure. And this is actually how we got the gas bubbles into the soda pop in the first place. We actually pressurized the chamber above the solution, put a bunch of CO2 bubbles in there, and that forces it into the solution. And so if you were to increase the pressure above the solution, if pressure increases, more of those gas particles get forced into the solution. The solute increases in concentration. Well, there's got to be some way to measure this, and good news there is. We call that Henry's law. Henry's law says that the solubility of a gas is going to be equal to Henry's constant for that particular gas. It is dependent on the gas, because all the gases are slightly different sizes. All of our gases have slightly different intermolecular forces, times the total pressure of that gas above the solution. So it's a pretty straightforward mathematical piece. We just got to make sure we've got kind of the right sets of information to be able to look at this. And good news, Henry's constant is just that. We have a great big old table of these. For each of our different gases, we have measured this constant. It is temperature dependent. As we said before, typically we say 25 degrees Celsius is kind of our normal temperature because that's what most room temperatures are at on a given day. And so that's how we get that kind of K. That'll always be provided for you unless I give you enough information for you to calculate that value. Typically though, we're going to give you that constant as an informational piece that you have. So then you would just need to either figure out what the solubility is based on the pressure, or if you know the solubility, work back to find the original pressure of the gas. Again, math is pretty straightforward. It's just putting those numbers in the correct place. Cool. So there's a practice problem for us. This is coming actually out of the PowerPoint. I tweaked it just a little bit. I wanted to try the harder of the two. Hope that's okay. I thought you'd be okay with that. Let's take a look at this problem. Make sure we know how to go about working a calculation like this. Cool. So as we're looking here, we've got the atmospheric pressure of a barometer. Remember, barometer reads the total pressure of our system. So the atmospheric pressure is 1.05 atmospheres. What is the solubility of a nitrogen in the solution at 25 degrees if nitrogen accounts for about 80% of the total atmosphere, specifically 78%? And this actually would be for example, something like a glass of water at sea level, right? Most of the atmosphere is nitrogen. So this is how we'd actually figure out how much of that inert nitrogen is actually dissolved into that solution. Well, we know a couple different pieces. We know the total pressure. We know the percentage of that pressure that is coming from the nitrogen. Okay, well, with those two pieces, we can actually go ahead and figure out what the partial pressure of just the nitrogen is. We would take our total pressure, 1.05 atmospheres. We could set up a ratio here, or we could also just multiply by the decimal form of our percent. So we're just taking that 78%, changing it into a decimal. I'm going to multiply that by the total pressure to figure out what actual proportion or part of that total is from just the nitrogen, because air is obviously a mixture of things. And so if we multiply those two values together, we find that the total pressure, or sorry, the partial pressure from just the nitrogen is 0.819 atmospheres. I'm going to hold on to all my values, all my numbers until the very end when I do my final rounding. Obviously, we know that there's only 2 sig figs here, but cool, we can kind of hold off. We got our formula here, which is kind of nice. It's pretty straightforward. We're trying to find the solubility of that gas. We now know the pressure of just the nitrogen, and we know the value for our Henry's constant for nitrogen at this particular temperature. So we can go ahead and actually set this up. We want to find the solubility of that gas. It's going to be that constant 7.0 times 10 to the negative fourth. Oh my goodness, those units. Moles per liter atmosphere. It's almost like it's a derived and or found value to make the math work. Okay, times the pressure from just the nitrogen, which was at 0.819 ATM. I'm leaving them all in here so you can see what happens here. Atmospheres cancel. We're left with moles over liters, which hopefully you recognize as molarity. So we multiply these two together. We get a solubility of our gas at 5.7 with 2 sig figs times 10 to the negative fourth molar or moles per liter. Cool, just a little bit of example with Henry's law. There's a couple practice problems for you on this. Make sure you're feeling okay on these, and we'll kind of keep on keeping on.